Okay, now it's being recorded. Okay, so today we're going to be talking about generics. And if you were in CSE 102 last year, this will be a topic we did not cover last year. If this is your third time, then we'll, or if you were in the class 2 years ago, then this will be a review of stuff from then. Okay, so let's go ahead and get to it. Okay, so one of the things that one of the important parts of this whole generic thing is, remember, one of the things that I've talked about in testing, but also in other parts of this this class and CSE 101 as well, is when we find errors can be very important, right? That ideally we would like to find errors and find problems in our code earlier rather than later. So remember that the worst case scenario, our worst case scenario, is if an error or if a problem in code is found by our users, right? We don't want our customers or our users to find it, because remember, what does that result in? Well, you know, the first problem that a lot of times we run across is our users have to have some kind of stoppage, right? Where either a patch has to be released, which means that they may be in the middle of working on something. I'm sure many of you have been in the middle of doing something when you've gotten this message from your from Windows or from Mac OS or whatever you're using, and it says you have to restart in order for this update, this patch, to be pushed through. And so that's kind of annoying. But the more often that happens, if that happens a lot, if our customers see errors a lot, then that results in them not having a lot of confidence in us, right? And that can result in lots of problems for us, for our company, stuff like that. So earlier is much better than later. And so we've talked about the 3 different types of errors. We've talked about the compiler error, the runtime error, and the logical error. And we also talked about how it's easier to find certain types of errors. It's easier to find the compiler error. In fact, usually we get a message right on the line where the semicolon is missing or something like that. Runtime errors can be a little bit harder, but sometimes we get a hint. The exception at least tells us where the exception happened. It may not tell us where the source of the error is, but it can at least give us a hint. Logical errors, we just kind of have to go back through the code and just kind of figure it out, because logical errors means the code ran all the way to the finish, ran all the way to completion, and we just ended up with different output than we expected, right? So if we can make sure that if an error is there, if we can find it during the compile time, that's the best situation for us, right? That's the best. That's the best as far as developers are concerned. That's the best time to find errors, because one, it tells us exactly where the problem is, and it's easier to fix. We haven't started running code or anything like that, and that's one of the benefits of generics. Okay, so you can read the objectives some other time, but basically, so remember this JDK Java Development Kit. Okay, so what's going to happen is when we go to try to compile this code, if you are learning Java using a JDK of 1.6 or greater, then what's going to happen is, and I can just go ahead and pull that up here, right? If I go to run this, if I go to compile this, okay, I'm going to get this compiler warning. Now, let's be clear, this is not a compiler error. This code compiled. In fact, if I go ahead and delete this, okay, and I go to compile it, right, it's still there, and I can still run it. In fact, actually, let me go ahead and add a line here. list.get 0. Okay. All right. So if I go ahead and compile this, right, and run it, it'll run, right? It'll run. There's no problem there, right? But I did get this compiler warning, and what that's saying is there's nothing syntax-wise, there's nothing syntactically wrong with your code, but there could be a problem. There could be an unsafe thing going on, right? And so we could recompile with this Excel int to find out, but basically we already know what the problem is. And the problem is that we're using this generic array list, which means we could put anything in there. Okay, so what if I said, okay, list.add, what's something other than a string? Well, maybe an integer, 23. Okay, so if I compile this, same thing. If I run this, same thing. All right, but notice that I was able to add something that wasn't the same type as the first thing. And you may be saying, well, especially if you have I think some of you in this class have programming experience in Python, and you'll say, oh, well, that's just like a list in Python. There's no problem with that. We can have a mixture of types. Okay, and yes, to some degree, what's the word? That ability to put multiple types in there, it could be helpful, but what happens if we try to sort this? If we try to sort this, well, which is greater, 23 or Java programming? Well, we don't really know because one's a string and one's a number. So how do you know which one is greater? How do you know which one is less? So that can be a problem when we try to use useful things like sorting, any type of comparison. What if we tried to pass things to a method? What if there was a method that needed to have a string as a parameter and we give it this, but then we try to go through the list giving other values? Well, it can be a big problem, right? If we try to pass an integer when a string is expected, then we could end up with some issues there. Okay. So generics force us to say, okay, we're not going to get a warning if we add this string identifier. So what we're saying is here, we're going to say this array list has to be a string. Okay. The types of items that are allowed to go in here are strings, and I'll show you one second. So we did get a compiler error, but the reason why was because we tried to add something that wasn't a string. So if we said get rid of that, compile it. Now notice, look, no compiler warning, no compiler error, and when we go to run it, it runs the same as before. Okay, so I can probably hear some of you thinking, or at least the way I might think if I were in your situation is, so why are we adding this extra typing when there was no real problem before? And again, what we want to avoid is we want to avoid getting errors later. Right? The compiler warning is there, so I'll go ahead and return this back to the way it was before because I want this one to be the one that's available on the Google Drive. Right? The compiler warning is there because it's saying that you're having this unsafe operation. You are allowing different data types in here, and you know, for what you have here, there's no error. There's no error for what you have in here, but that doesn't mean that there won't be an error later, an unexpected error later. And again, the worst thing that can happen is that our user finds out about this error later. Like they do something later on that we were not prepared for and that they find the error. Okay. So that's what we're trying to avoid, and that's why the compiler warning is there. Again, not a compiler error. This allows the code to compile. It allows it to run. The compiler warning tells us we may be doing something that may later result in an error of some kind. Okay, so the whole generic idea is we allow certain things like an array list, like a stack. We allow those things to force them into certain types or certain classes of types, because the one example we'll see in just a moment, if there's time today, if we don't have to push this off until tomorrow morning, one of the examples that we'll look at is where we can put a geometric object as a type there, and then anything that is a type of geometric object can be put in there. Okay. Actually, we did see that last week or 2 weeks ago. We saw that in some other examples. Okay. So again, we want to be able to detect potential errors at compile time rather than runtime. Remember, earlier is better. We find out errors earlier, and then we don't have to deal with them later. And again, we would prefer for us to find them. We would prefer for us to handle them. We do not want our users to find them and have some problems. Okay, so again, this is prior to JDK 1.5. I think the earlier slides are talking about 1.6. All right, but basically the comparable thing, if we were to try to compare this date to a string, we would get a runtime error. We would not get a compiler error. We would get a runtime error, and that's a problem. We don't want runtime errors. So now, if we try to compare a date to a string, the compiler tells us we can't do that. That's not allowed. Okay, so we force this C variable to hold a date object. All right, and when we compare it, to something else that's not a date, then that's going to tell us, hey, there's a problem. You can't do that. All right. Some different array list utilities. Notice basically it looks very similar, looks the same. The difference is that instead of just being a generic object, or sorry, let me not use that word, generic. Instead of it just being the object class over here, it's a generic, meaning that all of the things have to be the same type. So all of the things in an array list that we identify using the generic notation here, all of the things that are in our array list have to be instances of that type. Does that mean they all have to be objects of that specific type? No, it can be a child of that type. For example, if we had a parent class that was abstract, we can't have an object of that type, but we can have children that are all instances of that type. Okay. Cool thing, we don't have to cast, we don't have to do our own explicit casting. If we add something like this, 5.5 to an array list of type double, right? 5.5 automatically converted to it's a double object that has 5.5 as its value. Okay, and it can be converted both ways. That's the nice thing, is that it can be converted. This 5.5 is a primitive type that's automatically converted to an object. Then when we get that object and we try to put it into a primitive variable, it's automatically converted back. Okay. When we use this generic notation in here, like this has to be an object. This has to be a class. Okay, this cannot be, or it can be an interface, but it cannot be a primitive type. Okay, we cannot have an array list of primitive types. Oh, okay. Okay. One data data structure we'll talk about as an example here is the stack. Now the stack is sometimes referred to as a LIFO, an LIFO. Maybe I want to write that somewhere. Okay, LIFO type, and it stands for last in, first out. So if you think about it as kind of like a stack of, we would often refer to pancakes, or I think the Turkish word is krep, because it's like French-based thing. But when you put one on top of the other, right, then you can only remove the top one. You can't remove one from inside of there. Okay, even though my children might try to, because they say, oh, the ones that are deeper down in there, they're warmer and they've been kept warm, right? With a stacked data structure, you're not allowed to do that. If you put something on top of the stack, you have to pop from on top of the stack. You have to pop the last item that was put in. Okay, so push, we push to the stack, we pop, we get off the top element of the stack. Okay, and it returns the value. That's the top element. It returns the value, it returns the object. That's the top element, and it removes it from the stack. Okay, you'll talk more about this in your data structures class about how this looks and how this might be implemented in memory. It's a little bit beyond the scope of this class, but just the idea of understanding what a stack does and how it can work. Okay, so that's some examples that'll show up in our examples we'll look at in a moment. All right. We can use generics for methods where it's saying it's going to take an array of a specific type, right? And it will print those. Okay. Can do that with just an object array or with a generic array. Okay. Right, we can tell it that the generic that we use inside of this has to be of a certain type. We're bounding it. It's basically, we're saying that the E that gets passed here, all right, the E type here, it's going to be a type of geometric object. Does that mean that object 1 is specifically an object of type geometric object? No, it could be a square, or well, it could be a rectangle, it could be a circle, right? But it's going to be a child of geometric object in some way. Okay, so we can say we're forcing this to be of that type, okay, or of a child of that type. Okay. So basically, the raw type that we used, this basically the compiler kind of automatically made it look like this, right? Which is why we didn't get a compiler error, right? When we look back at this here, when we did it this way, are both of these objects? Yeah, we can make both of these into objects. A string is an object, right? String is a class, so that means that a string value is an object. 23, it got automatically cast to be an integer, integer object, right? So it got automatically cast to be an integer object and put into our list. So that's okay. There's no problem there. And that's why there was no compiler error. But the compiler was saying, when we went to compile it, the reason why we got that whole warning thing was because it was saying these two things, yeah, they're both children of the same parent class, the same parent object class, but there could be problems because they're not the same. They do not cannot compare to each other, right? So you could end up with problems later on. Okay, and this is why this is unsafe, right? Is that we cannot compare a string to a number, right? We would get a runtime error with this if we tried to compare, because even though both a string and a number are comparable objects, they are not comparable to each other. Okay, and we cannot return. Remember, see, we're trying to return 01. Well, that means that we're trying to create a method that could return two different types of objects. Okay, so if we say E extends comparable E, then what that means is that E, the thing we're passing, is going to have to be of a type of thing that's comparable to itself. So if we pass it a string first, the string is going to say, okay, am I comparable to a number? And the answer is no. And so then this will give us where this should result in a compiler error. Okay. I'm going to hold off on wildcard, the wildcard discussion till tomorrow, because I think we've talked about quite a few things today already. So what I'm going to do is I'm going to look at some of these, right? I'm going to look at some of these specifics, like the generic matrix. Let's actually, this is going down here. Okay, we're going to talk about the generic matrix for matrix arithmetic and how you can use generics along with a lot of the stuff that we've talked about already about inheritance and abstract classes and stuff like that for how we can implement this whole generic matrix thing. Okay, so the way this is going to look is, so the generic matrix, we're going to make it, it's going to be a data structure that holds a matrix. And it's going to hold objects of a generic. So we're going to have an objects of all certain types, right? So it can be any, what we're going to find out is we're only going to use them that they can be a number type. Okay. All right. Now we're going to have three abstract methods. Now remember this whole, when they're italics like this, it means that that is abstract. So we have an abstract class, we have an abstract method, and we're going to have this add two matrices together, right, and return another matrix. Right, so hopefully you guys remember from your math class how to do matrix arithmetic, how to add two matrices together, how to multiply two matrices together, how to zero a matrix. Right. Okay, so we're going to make these abstract in the generic matrix, because how we do that with an integer matrix versus a rational matrix, that's going to be two different ways of doing that. Okay. So, and those examples will show up in here, so we'll see them in just a moment. Okay, but I do want you to see how this UML diagram kind of plays out. Okay, so when we add two elements together, okay, so I said something a little bit different. I said something a little bit incorrect. The add and the multiply methods, they're abstract because it's adding two elements of the matrix together. It's multiplying two elements of the matrix together, and we'll see why those are abstract. Because you may be thinking, well, how you add and multiply should be the same based on numbers. It's just the plus sign or it's just the multiplication symbol. Right? But notice that the add matrix, multiply matrix methods, they're both concrete. So we will define them in the generic matrix class. We won't leave that to our subclasses to deal with. Okay. So then we'll take a look at those two examples. Okay. I'm going to go ahead and pull this up, but I do want to go ahead and just check back in on the class over here and see if there's any questions, if anybody's written anything. Does not look like you have. Okay. All right. So now what we'll do is we will move over onto the examples. We'll look at that, and then if there's no questions after that, then we'll call it a day. All right, so we'll kill this. All right. So we're going to do this whole generic matrix. Now we're going to say that the things that go inside, the objects that go inside of our matrix are going to have to all be types of numbers. Do they have to be integers, doubles? They could be either one of those. Could it be rationals? Now, if you remember from the rational discussion, I'll go ahead and pull that class up too, so you can see how what that one looks like. We notice that rational extends number. Good. Okay, and it implements the comparable rational interface, right? So rational is our own defined class. Now we know what a rational number is. It's defined as anything that can be represented as A divided by B, right? So it's anything that can be represented as a whole number A divided by some other whole number B. Okay, so we have a numerator, we have a denominator, right? If we don't seed it with anything, if we don't say anything, then we create a rational, which is a 0 divided by 1. Okay, so why not 0 divided by 0? Nothing can be divided by 0, right? So if we just construct it with nothing, if we just construct it with an empty, no arguments, then what we're saying is we want this to be represent the value 0, which, you know, for an integer type or a double type, that's kind of normal, right? That's, remember, what is the default value for an int? It's 0. What is the default value for a double or a float? It's also 0, 0.0, right? So this is basically saying default value for an object of this type, or a number of this type, 0. All right, so now what if we pass it a numerator and a denominator instead? What if we pass it values? Well, now what we're going to get is, well, first we're going to determine what the greatest common denominator is of these. And you might say, well, wait, why don't we just give it this numerator equals this numerator and denominator equals this denominator? I don't understand why we're going through this whole greatest common denominator thing. Well, basically what's happening is if we pass it values like 5 and 10, okay, what we don't want is we don't want this rational number. We don't want it to be seen as 5 over 10. We want it to be able to reduce to its most reduced form, which would be 1 over 2, right? That's what we're going to make it. So the greatest common denominator of 5 and 10, we get 5. Now, if it's positive, then it's 1. If the denominator is less than 0, then it's a negative 1, and we'll see why that all works out that way. All right, but it's the numerator divided by the greatest common denominator. So if we pass it the value 5 and the value 10, what's going to happen is that the numerator will get the value of 5 divided by 5, which is 1. Then the denominator will basically just be the denominator, the positive version of that, divided by whatever the greatest common denominator is. So what this does is it does a couple of different things. One, it would take 5 and 10 and make it into 1/2. Another example is it would take negative 5 and positive 10, and it would make it into a negative 1 over 2. Okay, so it would take this, because the denominator is positive, 10 is positive, it would make it a negative, sorry, it would make it a 1 times the numerator, which is negative 5, divided by 5. Okay, it would take, let's see, it would take if we passed it 5 and negative 10, what would happen is it would see this as less than 0. The denominator is less than 0, so it would take -1 multiplied by the numerator. So what this does is it would make it -1 over 2 over 2. So it forces that negative value to the numerator instead. Does that mean it makes a huge difference? It can, especially for arithmetic like addition, subtraction, and stuff like that, right? And then finally, if we passed it -5 and -10, then what would happen? It would give us a value of -1 times -5 divided by 5 would be 1 over 2, which is what we would expect. Okay, so basically what this does is it reduces it to its lowest form and forces, if there's a negative, if it represents a negative number, then it forces that negative to be associated with the numerator rather than the denominator. Okay, all right. We won't go into all the other details about how to find the greatest common denominator. I just wanted you guys to understand why this wasn't just taking this value and putting it in here, this value putting it in here, is because it's about reducing it to lowest forms and forcing the negative number to the numerator value. Okay. All right. All right. So that's for the rational, for when we get to the rational matrix. But let's go back briefly. Let's go back to the whole generic matrix concept. Okay, so the add, multiply, and zero values for our individual items inside of our matrix. Okay, the add, multiply, and zero, those are going to be things we're going to push off to our children to define. And the reason why is because the way that we're going to add different types of numbers will be different. The way we add two rational numbers, our self-defined rational numbers, will be different from how we add two integers, for example, or multiply two integers. And we'll see that in practice in just a moment. Okay, but if we have these add and define methods defined up here, all right, then we can use them to be able to add a matrix together or to multiply a matrix together. Because notice that if we had defined this, let's say this had been defined as O1 plus O2, right? If that had been defined as this, then we could have just added each individual matrix value together, every crossing of ij, ij. Right? We could have just added them together using a plus sign. But that may not be how we add all types of numbers together. For example, we'll see in a moment that rational adds differently than integers. Okay, but had this been defined, we could have just used it that way. Now, one of the things that this points out is we can use abstract methods inside of concrete methods. That's okay, because this method in generic matrix, since we won't ever create a generic matrix object, right? That means that even though this method isn't defined here, when we go to use this, when we go to use a rational matrix or an integer matrix, when it goes to call the add matrix method, it will have access to a defined add method, okay? Because these methods will be used, will exist inside of our classes here. Okay? So we can use this method, even though it's abstract here, we can use this inside of a concrete method here. Same thing with the multiply. Okay. Now, I won't go into a large discussion of this add matrix method. You guys, again, if you know matrix arithmetic, how to add and multiply two matrices together and get a resulting matrix, okay, that should be part of your math class. I hope your math instructor knows how to do all that and has taught you how to do all that. All right. So we won't go into a great discussion about that, but some of this stuff should be understood by if certain lengths, y matrix.length, y matrix 0.length, what does that represent? Okay, why we're throwing an exception instead of displaying something to the screen instead of ending the program, that kind of thing. Okay, all right. Well, it is ending the program. Well, we're not using a system.exit type of thing. Okay, how to multiply two matrices together and all that. All right, so let's then talk about the addition here, the add and multiply methods. Let's go with the easier one first, the integer. All right, so to add two integers together, we can just use the plus. Okay, we can just use the plus sign. Remember, what's going to happen is that this will automatically get cast to the primitive integer type. This will automatically get cast to the primitive integer type. They will then be, those values will be added together, and then what will happen? It'll return the sum of those two values, which, because it's an integer return type, will automatically get cast to an integer object. Okay, same thing with the multiply, right? And what is the value of 0 for an integer? It's just the value of 0. Okay, so this is pretty easy. This is pretty straightforward. Okay. But when we go to add two rational values, we can't just, because it's an object, because it's a special object that we've created, we define our own representation of what that means to add two numbers together. Okay, now if we go back and look at the rational class, add, right, it's basically a lot of this of how to get the new numerator, the new denominator, right? It's basically cross producting. It's multiplying first numerator by the second denominator and the first denominator by the second numerator, and then adding those two together and then giving me a new denominator that's the multiplication of the two. Okay, this is my oldest son actually is going through this right now in his 5th grade class, so hopefully you guys understand why this results in a correct addition of these two numbers. Okay, same thing with the multiplying. Okay, why we multiply the two numerators together, we multiply the two denominators together, and then we create a new rational object with that new numerator and that new denominator. And remember, the nice thing about what we did in our constructor, right, where we did this whole greatest common denominator to reduce it to lowest terms and all that, the nice thing about that means we don't have to do that here. We can just say, okay, you know what? We're just going to take, for example, right here. If we give it 3 divided by 5 and we add to it, 5 divided by 6, for example, right? That's just going to create a new rational object that's whatever 18 plus 25 is divided by 30. Right, that should be right? Now this is going to end up in a prime number up here, so it's not going to be reduced at all. But if this had resulted in something else, in some value that is divisible by this, right, then what would have happened is all of that would have been caught up, all that would have been caught to make reduced form down here in the constructor. Okay, down in the constructor when we called it here. Okay, I hope that's not too confusing. I kind of think I may have used a bad example here. Is there another? Let's see, 18 plus. Let's maybe say 22. Let's go. Yeah. we'll figure this out later. I'll come up with another example. I'll get my son to help me come up with a better example for later. Okay. All right. Same thing with multiplication though. When we just take the two numerators, multiply them together, take the two denominators, multiply them together, we create a new rational object that is lowest forms. All right, the lowest form, and we return that. We just return that new object. Okay. So what happens is that in the rational matrix, we use that add method and that multiply method, and we return a new rational object. Remember, we can't just return 0, right? Because this is not an object, or at least it cannot be cast to an object of the rational type, right? What we do is we return the equivalent of 0 in the rational form. Okay. Could we have also have done this? Absolutely. This would have worked as well too, because why? Because in the no argument constructor, that is what we created. Okay. So both of those would have been equivalent. Okay. So what happens if I create a rational matrix, if I create two rational matrices and I go to call the add matrix method, it's going to call the add method. Well, the add method in generic is abstract, but the add method here in rational matrix is not. It's a concrete method. It's a concrete implementation of the abstract method from generic matrix. All right, so let's do a test on both of those. Okay. So here we're going to create two matrices, two 3x3s, right? And if we're going to see what happens when we add them together, and we're going to see what happens when we multiply them together. Okay. And the print result method is going to get called from the generic matrix, which basically should just display them using this whole we'll see how that works. I'll let you kind of parse through it to see why it does what it does and later. Okay, it's kind of running out of time for today. Okay. All right. So if we run this, let me debug first. Okay. So we're getting this 2x2 array. All right. Oh, I didn't mean to step in. Okay. So now we're going to say, what is the first matrix plus the second? So what's going to happen is it's going to take this 3x3 array, and it's going to try to add the two matrices together. Okay, now the matrix 1, was our 1, 2, 3, 4, 5, 6, 1, 1, 1, right? 1, 2, 3, 4, 5, 6, 1, 1, 1, right? Okay. So we're going to create this new result based on the this result variable based on the two types of numbers. Now remember what I said before was that we can make this anything that is a child of this, right? So it extends number, so it must be able to be a number. Is an integer a number? And the answer, of course, is yes, it is. Okay. So we can put the integer into there, right? So now what we're going to do is every time through, we're going to add the value at I, the value at j together. Well, we're going to add this plus this, right? And we should get the result. Right now it's nothing, but as soon as this gets done, we should get 2 there, right? 1 plus 1, right? And then when we step through it again, we should get 3, which is 2 plus 1. And then we should get what? 4, right? So we're going to do this 9 times, right? We're going to do this 1 time for each pair of values. Right, so this plus this. Then we're going to go through and do the next row, all 3 columns of the next row. Then we're going to go through all 3 columns of the final row. So if we do this 9 times, right? And now we should return this, right? So M1 plus M2 is, we're going to print, right? So this was our first matrix, right? This was our second, and we added them together, right? Similar thing with multiply. When we multiply M1 and M2 together, then we should end up with oh, that's the print result. I didn't mean to do that. Oh, there it is right there. Okay, it was just below. All right. So when we multiply these two together, right? So we multiply row by column, row by column, row by column to get each individual value, right? Okay. So I think this is correct. It's been a long time since I've done matrix multiplication, matrix addition, right? So this is how we would do the integer matrix, right? We can create 2 arrays that are 3 by 3, right? And then we can add them together. Now, what happens if one of these is a different size than the other, right? Now what should happen? No compiler error, right? There shouldn't be any compiler error. But if we run it, then what should happen is we should get an error here when we try to add these two together, right? Because they're 2 different sizes, right? And we actually, what we did was we threw an exception. This wasn't a way that we got a runtime error, right? The matrices do not have the same size. Okay. I'll return these back to their form as they were before. Build and run, and everything should be fine. Okay. So notice that the test rational matrix, for the most part, is going to be basically very similar. The only difference is that the way we create the arrays is going to be slightly different because we're creating an array using I and j values. All right. But as far as using the add and multiply, they're the exact same thing, right? This and this are the exact same thing, right? Okay. All right, so when we go to run this, there's no difference, right? There's no difference in how it executes. The same add matrix method is called, right? Because it's calling this add matrix method, the one from the generic. The differences are, one, for this one's, the visual difference is the one that's obvious, is how we created the 2 arrays. It's very different. The other difference is that in this add matrix method, we call the same method here, but this, because one is the integer matrix and one is the rational matrix, the add method is different. So if we look here, okay, so when I step in here, notice that the same add matrix method from the generic matrix class is called, but when I go to add the two values, the add method that gets called is this one instead, is the one from the rational matrix. Okay. All right. So the just go ahead and go to the end. Okay. The main thing I want you to take away from this, the main thing that I think is important, is a couple of different things. One is that we can force our data structure, or we can force a method or an array list or an array. We can force them to have a specific type or a specific class of objects. Okay, so like for example, here in the generic matrix, we require that anything that gets put in here has to be of a number type. So it can be something we created ourselves that extends number. It can be something that exists already in Java that extends number. Okay, so we can force that to happen. And if we try to create a matrix of something other than, if we tried to create, for example, here, let's say string. Okay. I'm going to get this problem, right? I'm going to get this 8. You can't do that because string is not a number. So you can't do that, right? But I can do rational because rational extends number. So rational is a type of number, so it's okay. All right. So that's one takeaway I want you to have from this, is that we can force a specific type or a specific class or a specific parent class to be used. Okay. The other is, as we saw here, I can use abstract methods inside of concrete methods because I know that when this thing actually gets executed, if this method, add matrix, ever gets executed, it's going to be executed using something that's concretely defined, right? I know that I cannot execute add matrix unless add is defined. This cannot be executed on just a generic matrix object because there cannot exist a generic matrix object because it's abstract. Okay. Oh, and I guess one more takeaway I did want you to get from this was yet again a reminder of how UML fits into all this, of how we use UML to define how things are related to each other. So in this particular example, this was an abstract parent class that has 2 children defined in our system. Okay, so I'm going to unshare the screen. I'm going to go back over here. All right, let's see. So does anybody have any questions before we end? You can either ask by unmuting your microphone, or you can ask on the chat side. Because if not, then we will end for today, and I will see you tomorrow at the normal time. The new normal time, the 10:30 is when we're starting. Okay. All right. Stop the recording, and I'll end the meeting.